Welcome to Spring LIB.
Hi everyone. So what we have today is a problem that has a rod OA that's rotating counterclockwise about a point with angular velocity theta dot equal to 5 radians per second. The contour of the path is given by this equation right here. R is equal to 1.5 times the quantity 2 minus cosine theta. And we have two collars with the mass 0.75. And what we're asked to solve for is the normal force exerted when the theta, or the angle of rotation, is equal to 120 degrees. And the way we're going to be solving this problem is by using our knowledge of rotational, so tangential and normal acceleration and velocities, and combining that equation of motion with Newton's second law and with our free body diagrams. So let's go ahead and get started. So what we can do first is solve for our theta dots, or basically our acceleration in the radial and theta directions. So what we can do is we can take our equation, r equal to 1.5 times 2 minus cos theta, and solve for that when theta is equal to 120 degrees. So when we plug in 120 for theta, we see that r is equal to 3.75 feet. Next, what we can do is take the derivative of r and say that r dot is equal to 1.5 sine theta times theta dot, and evaluate that at theta equal to 120 degrees. And we find that r dot is equal to 6.495 feet per second. We can again take the derivative and say that r double dot, the acceleration in r, is equal to 1.5 times the quantity sine theta times theta dot plus cosine theta times theta dot squared. And we'll see that this is equal to negative 18.75 feet per second squared. Next, what we can do is we can go ahead and solve for acceleration in the radial direction. And we can say that that's AR, which is equal to r double dot minus r theta dot squared. And we actually know all of these quantities, and we can get an acceleration in the radial direction equal to negative 112.5 feet per second squared. We can also solve for acceleration in the theta direction, because this is equal to r theta double dot plus 2r dot theta dot. And we see that this is equal to 64.952 feet per second squared. Next, what we're going to do is we're going to go ahead and do our equations of motion. So first, we're actually going to define another angle, psi, that is going to be defined such that here's our plane and here's our path. And psi is the angle between the tangent to the curve and r. So that's this angle here. And this is r, which is equal to 1.5 times 2 minus cosine theta. And we can use this by saying that tan of psi is equal to r divided by dr d theta. And evaluating this at theta equal to 120 degrees gives us that tan of psi is equal to 2.8867. Therefore, we see, or we can solve for, that psi is in fact equal to 70.89 degrees. And this is going to be very useful for us in our free body diagram. So our free body diagram looks like this. Here are our axes. There's our r-axis, and here is our theta axis. And here's our collar. We're just going to signify that with a dot. So here is our angle psi. And here we have our normal force, which is acting on the collar. And then we also have the force that is exerted from the rod rotating. So with knowing that this is psi, we see that this is equal to 90 minus psi, and that is equal to 19.11 degrees. So applying Newton's second law, we see that the net force in the radial direction, which is equal to m times acceleration in r, is equal to negative cos 90 minus psi, or negative n times, excuse me, change this up a little bit, is going to be equal to negative n times cos of 90 minus psi. What we can do is we can actually go ahead and plug in for m and ar. So we know that we know the weight, which is equal to 0.75 pounds. So we can say that the mass is equal to 0.75 divided by 32.2, which is the acceleration in feet per second squared, times ar, which we saw for above, which we know to be negative 112.5 feet per second squared. And that's equal to negative n cos 19.1 degrees. So we can go ahead and isolate n, as that's our only unknown, and we see that our normal force is just equal to 2.77 pounds. And that's our final answer.